So now we want to answer the question of why have we talked about entropy with the second law of thermodynamics? So the second law of thermodynamics tells us that the entropy of the universe never decreases. Okay? So if you take the entire universe, everything that exists, and you were to be able to calculate the value of the entropy of the universe, it will never get lower than that. What that means, for anything that ever happens in the world, that process has to increase or not change the entropy of the universe. There are no processes that happen that decrease the entropy of the universe. That means spontaneous processes correspond with an increase or not change of the overall entropy of the universe. So you'll note there's that equal to. You can have processes that happen that just don't change the entropy of the universe. But you can't go down. You can't go negative. So spontaneous processes are things that happen. And so what that means is everything that happens corresponds to an increase in the entropy of the universe. So that's another thing to focus in on. We are talking about the entropy of the universe, not just some molecules. And so this is what we're going to be able to use to predict the spontaneity of a chemical reaction. Does the chemical reaction increase the entropy of the universe? Then it happens. Does the chemical reaction decrease the entropy? Would its happening decrease the entropy of the universe? Then it's not happening, right? Then it will not happen. And so when you go through these processes that increase the entropy of the universe, these spontaneous processes, these are things that happen, right? If that forward process, it occurring, corresponded to an increase in the entropy of the universe, that means the reverse of that process is impossible, because the reverse would decrease the entropy of the universe. So all of these processes, food coloring spreading out within water, that diffusion, that is an irreversible process. It does not happen. It doesn't matter how long or how much you try, you're not undoing this. Falling off a diving board, you just fall. You don't unfall, right? You can climb back up the diving board, but that's a different process. You can't just say hop out of the water and spontaneously make it all the way up to the top of the diving board. Heat always flows from hot to cold. If you just put a piece of metal in, say, water right here, you would never expect the water just to get hot, the piece of metal just to get hot and the water to get cold. You never have just spontaneous temperature imbalances, right? Those are irreversible processes. They don't happen. You are instinctively aware of the second law of thermodynamics. You can tell that this GIF is showing a process in reverse. That is not something that happens. It looks unnatural because it is. Entropy in the second law tells us kind of what the flow of things in the universe is. You can tell this looks unnatural. The seeds hop up onto the popsicle. That doesn't happen. That is a decrease. That would be a decrease in the entropy of the universe. You can tell it looks wrong. This diver who pops out of the water and then just flips all the way up to the top of the diving board. It looks wrong because it is, right? That is not naturally occurring, because that process of leaving the water and popping up onto the diving board would be the opposite of, would correspond to a decrease in the entropy of the universe. It's not going to happen. This dog putting a piece of pizza back onto the table, right? You can really see right there, that looks super weird, right? Where it flips up. Now you will notice when the dog is kind of pushing the pizza, like right here, that doesn't look that crazy, right? That is a relatively small increase in the entropy of the universe when he's pulling the pizza. And that's why pushing the pizza doesn't look that crazy, because that is not that sort of irreversible. It is less irreversible of a process. And so these sorts of, kind of falling off a 40-foot platform, very irreversible. But, kind of in pulling the pizza off where the pizza falls, but sliding a pizza along the plate, that's going to be pretty reversible because it's a smaller value of the change in the entropy of the whole universe. I can just watch these GIFs all day. All right, so Delta S universe is what the second law of thermodynamics describes. Okay, that we know that value always increases. That's a little cumbersome because generally we're interested in chemical reactions. And so what that means is if I want to know the change in entropy of the universe, then I need to can figure out and compute the change in the entropy due to the chemical reaction. So that's what we talked about predicting the sign of previously. The fact that going from, say, a liquid to a gas increases, or say a gas to a solid decreases. But if we want to figure out spontaneity, we're going to need to understand or account for how the reaction affects the surroundings. Okay, how does that happen? One of the important aspects of this is that the only thing that can never be negative is delta S universe. Delta S of the reaction and delta S of the surroundings can definitely be negative. They have to just combine together to give you a non-zero or a zero or positive value. So, you know, the chemical reaction, if say you're doing it in solution, or say the melting of this ice cube, there's an entropy change of the ice cube, but there's also an entropy change of all the water that was already in the cup, right? How has the entropy of that changed? And it's definitely changing, you know, based on, or it's being affected by the ice melting in it. And so we want to account for both of those effects, you know, kind of the how does the chemical reaction entropy change, and how does that chemical reaction happening affect the surroundings? Generally, the solvent, we do a lot of aqueous chemistry, or the air around it, chemical reaction, or say the beaker it's in. We generally don't need to be too concerned if you're doing, say, a chemical reaction in Baytown as to how it affects, say, the air in Seattle. There's probably not a good even conductor, even in Houston, you know, very far away, it's not really going to be affecting it. It's really that kind of local effect on the surroundings. If you start dealing with, like, you know, things in the atmosphere, those are much larger scales. But locally in the lab, we're really focusing on, say, the solvent or the air around our reaction. So again, when we look at these kind of processes, we can start to also understand what is easier or what is more likely to happen. We know that delta S tends to be positive. For the universe, that would be spontaneous. When we look at the system kind of focus, it still does kind of show us what we're looking at, that delta S of the system being positive is easier. This is more spontaneous. If you just don't care about your kitchen, it'll end up looking like this. A lower entropy system requires work. You have to try to make this ordered, right? Because there's only a small number of ways that it's possible, so you have to put in work. It's still possible. It can still happen. You can pick this up. God help you. But you can pick up this mess in this kitchen. It's possible. And so it is possible to decrease the entropy of a system because you can account for basically the overall increase in the surroundings. And, you know, one of the ways that we can kind of understand the second law of thermodynamics is that atoms and molecules move via random motion. They just kind of bounce around. Molecules move around, they collide with each other. Collision theory, they just randomly collide with each other. And sometimes, hey, you got a chemical reaction. And that's all just happening randomly. And so if they're just randomly changing, the ultimate kind of what you're going to view, the ultimate output or products of, say, chemicals changing is going to be a pretty random outcome. And so the outcomes that are most disordered, there's a lot of ways that they can happen. And so if you're just kind of changing randomly, you just randomly pick an outcome of, say, a bunch of chemicals mixed and interacted, the most random outcome is probably just, it has just a lot of possibilities. There's a lot of ways that that can exist. So raw probability, you just end up with one of those random outcomes. And when you start dealing with moles and moles of atoms, there's just a lot of kind of randomness. You just end up with whatever that most likely outcome is, which is going to be the most disordered outcome. All right, another video looking for more questions on participation 324. I'll see you in the next video. We're going to start doing calculations.